This problem here is so classic on the AP the calculus exams that I obviously had to do a video on it. And it's a related rate involving water being emptied from a conical tank. It's just such a classic that I promise this won't be the last time you see it. So this is water is being emptied from a conical tank at 12 cubic meters per minute. The tank stands vertex down and has a height of 8 meters and a base diameter of 6 meters. How fast is the water level changing when the water is 4 meters deep? So the first thing we want to do is we want to model this with a diagram. So here's my conical tank, and there's water in it, and it's being drained, and the height of this cone, it says, is 8 meters. And it says that the base diameter is 6 meters. I'm going to label the radius because usually the radius is more likely to be involved in any type of formula. All right, so there are the dimensions of my tank, and we're asked to find a rate. How fast is the water level changing when the water is 4 meters deep? So let's take note of what we know and what we want. So we know that the water is being emptied from the tank at 12 cubic meters per minute, and since that's a change in volume, I'm going to label that the change in the volume with respect to time, dV dt. Now since it's being emptied, that means we're losing volume, so I'm going to write it as negative 12 cubic meters per minute. And what we want how fast is the water level changing when the water is 4 meters deep. So let's go to this. Let's take a look at the water. Actually, the water level. So the water level is changing. So this here, I got to label this as a variable. I'm going to call this H, and I'm going to call this R. And in fact, I might even erase this R up here, so because that's actually not a right. The radius is 3 meters, but as a variable, we wanted to call that the top of the water cone there. That needs to be R. So what we actually want, because we're asked to find how fast the water level is changing, we actually want dH dt. And we want that when the water level is 4 meters deep. So we want dH dt when H is 4. Alright, so now what we need to do is we need our equation that relates the variables we're interested in, that are involved in the problem. So obviously we need H to be in there, and we need V because that's a rate we know. So let's remind ourselves what the formula for volume of a cone is. It's 1/3 pi r, 1/3 pi r squared times the height. Now, there are a couple options at this point. The first thing is please don't substitute any variables in yet. All right, you have to take a derivative first. But the second thing is the issue here is that the volume is expressed in terms of two variables, r and h. It would be great if we could somehow make a substitution so that it's only in terms of one variable. That's usually going to be more convenient. It's going to make the problem a little easier. So what kind of relationships could we get between h and r? Because we want to substitute one of them. And in fact, I probably want to replace the r because then the volume will be in terms of the height, and then it'll help me find dH dt. So I'm going to zoom in. I'm going to actually draw a vertical line in that cone, and I'm going to go over here, and I'm going to analyze that right triangle I just made. So the top here, that's 3 meters. The height here is 8. And what I've done here is I've said, okay, well then, when as the water level changes, that R and that H change. Now this is where some of your geometry might want to, or it might be useful. We can make a proportion here because the base of the one leg of this triangle divided by the other leg is always going to be R over H. So 3/8 is R over H. Okay, and so what we can say is we can say that R equals 3/8 H. Alright, so now I can plug that in to my formula. Right here. So that means that the volume is equal to 1/3 pi 3/8 H squared times H. And I'll clean that up a little bit. That means it's 1/3 9 over 64 H squared times H, which means that the volume is 3 over 64 H cubed. I missed a pi in there. Let's put the pi there, and we'll put the pi there. Alright, so now is when we need to take the derivative with respect to time. So the derivative of the volume would be dv dt. The derivative of this right term, we'd use the power rule. Don't forget pi is a constant, it's not a variable. So it's going to be 9 pi over 64 times h squared times dh dt. Okay, and so now what we can do is we can substitute in our known value. So I'm going to write solve and substitute, or substitute and solve. I know that dv dt is negative 12, so now I know that I can write negative 12 equals 9 pi divided by 64. Now, again, I'm trying to find dh dt. That means there should be some way for me to find h, right? Well, at the instant that h is 4, because that's when we want to find this rate of change, when h is 4, so I can plug that right in. And now I can solve this equation for dh dt. So if let's see, so this is negative 12 equals, this here is a 16, so 16, 9 pi over 64 times 16 times dh dt, and this turns into a 4. So now I'm going to multiply both sides by 4 over 9 pi times negative 12. That's dh dt, which means it's, let's see, negative 16 over 3 pi. And if you put that in your calculator, it's about equal to negative 1.697. Alright, so now we can interpret and we'll be done. By the way, notice it makes sense that it's negative because you're losing the water level is decreasing, so you're losing height there. So we can say at this instant the water level is decreasing That's negative 1.697 meters per minute.